Right now, place a glass of water next to your bed and look at it as a measured volume, not as a drink. 250 milliliters, 1 cup, about the volume of a small hydraulic reservoir. If you swallow it in the last minutes before sleep, you are not simply wetting your throat. You are adding mass to a closed circulating system, changing the pressure signal inside your blood vessels, changing the electrical firing of sensors in your brain, changing the valve settings inside your kidneys, and loading a stretch sensor in your pelvis while your sleep machinery is trying to shut itself down. One glass, several circuits. The mistake is thinking water is passive. Water is treated like background material, like the body is a container, and the water simply fills it. That is not how the system works. In a living machine, water is pressure, solvent, coolant, signal carrier, and volume control. It determines how easily blood moves through a tube. It determines how concentrated sodium becomes around a neuron. It determines whether a hormone is released from the posterior pituitary or held back. It determines whether the kidney opens microscopic channels or removes them from the membrane. It even determines whether your bladder sends a low-voltage warning pulse into the sleeping brain at 2:17 in the morning. The glass reaches your stomach first, but the stomach is not the main intake valve. It is a holding chamber. Water begins moving onward into the small intestine, where the real absorption surface is folded into villi and microvilli, turning a narrow tube into a large exchange interface. From there, water follows osmotic gradients into the bloodstream. No pump is pushing each molecule one by one. The driving force is concentration. Sodium, glucose, amino acids, and other solutes create gradients, and water moves, because physics allows no other stable arrangement. The body does not command water, it creates conditions, and water obeys them. Within minutes, plasma osmolality begins to shift. Osmolality is not a wellness word, it is a measurement of particle concentration, usually expressed in milliosmoles per kilogram of water. Human plasma is normally held in a narrow range, roughly around 280 to 295 milliosmoles per kilogram. That range matters because cells are bags of charged chemistry separated from the outside world by thin lipid membranes. If the fluid outside a cell becomes too concentrated, water leaves the cell and the cell shrinks. If the fluid outside becomes too diluted, water enters and the cell swells. A neuron does not tolerate uncontrolled swelling. Its geometry is part of its function. The brain has sensors for this specialized osmoreceptive neurons, monitor the concentration of the blood, and help regulate thirst and arginine vasopressin release. These sensors are not philosophical, they are strain gauges. As extracellular fluid becomes more concentrated, water leaves the osmoreceptor cells. Their membranes deform, ion channels change, and firing patterns shift. The signal goes into the hypothalamic control system. When water is scarce, thirst rises, and vasopressin rises. When water arrives, the signal relaxes, the voltage changes, the valve command changes. Vasopressin is the first major switch affected by drinking water before bed. It is also called antidiuretic hormone, which is a crude name for a precise control signal. It is produced in neurons of the hypothalamus, stored in the posterior pituitary, and released into the blood when the system needs to conserve water. Its target is the kidney, especially the collecting duct. There, vasopressin binds to V2 receptors on principal cells. That receptor activates cyclic AMP and protein kinase A, and the cell moves aquaporin 2 water channels into the apical membrane. The duct becomes more permeable. Water that would have become urine is pulled back into the body. The urine becomes smaller in volume and more concentrated. Less water leaves the machine. This is not a metaphorical valve, it is a molecular valve. Aquaporin 2 is a protein channel, and the kidney can insert it or retrieve it. When vasopressin is high, more channels are placed in the membrane. When vasopressin drops, those channels are removed. The difference is not cosmetic. Vasopressin can raise collecting duct water permeability by a large factor, because the membrane changes from a low-flow barrier into a controlled water passage. The kidney is not just a filter. It is a variable permeability recycling plant with hormone-controlled gates. At night, this control system is supposed to change mode. Sleep is not just the brain turning down consciousness. Sleep is a scheduled maintenance interval in which multiple subsystems shift their timing. Melatonin rises, core temperature trends downward, sympathetic output usually falls, and urine production is supposed to be reduced. Part of that reduction depends on the nighttime pattern of vasopressin. Under normal conditions, the body tries to keep the hydraulic plant quiet during sleep. It tries not to fill the bladder too fast. It tries not to wake the operator. This is why the timing of the glass matters. Drinking the same volume at 3 in the afternoon and drinking it 10 minutes before lying down are not equivalent inputs. In the afternoon, the system has hours of movement, breathing, sweating, eating, posture changes, and kidney filtration to distribute the load. At bedtime, the machine is transitioning into low output mode. You add water just as the kidney is being instructed to conserve water, just as the brain is lowering arousal, just as the bladder is expected to remain silent for several hours. The water arrives during a phase change. But the body does not send all of that glass to the bladder immediately. That is another oversimplification. Some of it expands the extracellular fluid compartment, some of it dilutes plasma slightly. Some of it changes vasopressin signaling. Some of it is held, for a time, inside the circulating volume. Some of it will eventually be filtered through the kidneys. The delay depends on your hydration before drinking, salt intake, kidney function, room temperature, sweating, alcohol, caffeine, medication, age, and how full your bladder already was. The same glass is not the same signal in two bodies. If you are dehydrated before bed, the glass can reduce a real deficit. During sleep, water continues. Leaving the body, it leaves through respiration as humidified air. It leaves through skin as insensible water loss. It leaves even when you are not sweating in any obvious way. A 2026 PLOS 1 paper by Kosuke Kaida and colleagues stated that 400 to 700 milliliters of water can evaporate from the body during a night of sleep. That is not water you choose to spend. It is operating loss from keeping warm tissue connected to air. This is the argument in favor of water before bed. A dry system runs with higher concentration gradients. Plasma becomes slightly more concentrated. Mucous membranes dry. The mouth becomes sticky because salivary output changes. Blood volume can fall enough to increase cardiovascular strain in vulnerable conditions. The brain may register thirst after waking. In this condition, a modest amount of water before sleep is not a mistake. It is a correction. It replaces part of the expected overnight loss before the long interval without intake begins. Now the evidence calibration, the direct evidence that a small bedtime drink improves every person's sleep is weak. The evidence that the body loses water overnight is stronger. The evidence that dehydration and sleep are linked is suggestive, but not mechanically complete. A Penn State-led study published in Sleep analyzed adults in the United States and China, and found that people reporting 6 hours of sleep had higher odds of inadequate hydration than those reporting 8 hours, with odds ratios reported around 1.59 in a healthier U.S. subset and 1.42 among Chinese adults sleeping 6 hours. That does not prove that drinking water before bed fixes sleep. It proves the sleep hydration circuit is real enough to measure in populations. But there is a second mechanism operating at the same time, and it works against the first. The bladder is a storage chamber, with sensors embedded in its wall. As urine enters, the bladder wall stretches. Stretch activates afferent nerves that send information through the pelvic nerves and spinal cord toward the brainstem and higher centers. During waking life, you can suppress the signal for a time. During sleep, suppression depends on the depth and stability of sleep. The bladder does not need to be full to disturb you. It needs to send a signal strong enough to cross the arousal threshold. The arousal threshold is not fixed. Deep non-REM sleep is harder to interrupt. Light sleep is easier to interrupt. Alcohol lowers sleep quality and changes urine production. Caffeine can increase bladder activity and has diuretic effects. Older age often brings lighter sleep and altered circadian hormone output. Sleep apnea can create repeated pressure changes in the chest that affect cardiac stretch hormones and urine production. A young person may drink 250 milliliters and sleep through the hydraulic consequences. Another person may drink the same amount and create one perfectly timed interruption in the first half of the night. That interruption is not trivial. Sleep is structured in cycles. A normal night moves through non-REM stages and REM stages in repeated architecture, roughly every 90 minutes, though the timing varies. Waking to urinate is not just a pause, it forces a state transition. Muscles activate, heart rate changes, blood pressure rises. Light hits the retina if you turn on a lamp or look at a phone. The brain moves from a closed-loop internal maintenance state into external control, then it must re-enter sleep. The cost is not the 2 minutes in the bathroom, the cost is the broken sequence. This is why nocturia matters beyond inconvenience. Clinical references define nocturia as waking at night to void, and they repeatedly emphasize that 2 or more nightly voids are often enough to become bothersome and worth evaluating. Excess evening fluid, caffeine, alcohol, diabetes, kidney disease, diuretic medications, hypertension, sleep apnea, prostate enlargement, overactive bladder, and leg edema can all contribute. The advice to limit fluid intake in the late evening, especially in the 2 hours before bed, comes from this mechanical problem. The bladder can become the alarm clock, but the bladder is only one chamber. There is another reservoir many people ignore, the legs during the day. Gravity pulls fluid downward. The veins and tissues of the lower legs can hold extra fluid, especially after long-standing, high salt intake, venous insufficiency, heart failure, or certain medications. When you lie down, gravity changes direction relative to the body. The legs are no longer below the heart in the same way. Fluid returns to the central circulation. The heart sees more volume. The atria stretch. Stretch can increase atrial natriuretic peptide, a hormone that tells the kidney to excrete sodium and water. The body converts yesterday's standing into tonight's urine. This is the supine fluid shift. It explains why someone can drink very little after dinner and still wake to urinate. The water was already in the system, stored in the lower body tissue compartment. Lying down brings it back to the central pipes. The kidney sees the volume and begins output. Add a large glass of water before bed on top of that, and you are not just adding one input, you are combining two reservoirs, the swallowed reservoir and the leg reservoir. The bladder receives the sum later, after you have already entered sleep. Now think about the kidney itself. Each kidney contains about 1 million nephrons, each a small filtration and processing unit. Blood enters the glomerulus under pressure. Fluid is pushed across a filtration barrier into the tubular system. The body then takes back most of what it filtered. Sodium is reclaimed. Glucose is reclaimed. Water follows gradients. Urea contributes to the medullary concentration gradient. The loop of Henle and collecting duct create the geometry required for concentration. This is not a drain pipe. It is a countercurrent engineering system. At bedtime, that system must solve a constraint problem. It must keep plasma sodium within a tight range, keep blood pressure stable, avoid dehydration during 7 or 8 hours without drinking, avoid overfilling the bladder, and maintain sleep continuity. The solution depends on input timing. If you go to bed underhydrated, the system has too little water and must conserve aggressively. If you go to bed overhydrated, it must excrete, but excretion threatens sleep. The optimal point is not maximum water, it is stable water. The machine wants balance, not abundance. This is where popular advice fails. Drink water before bed is incomplete. Never drink water before bed is also incomplete. The variable is not water alone. The variable is timing multiplied by volume, multiplied by current hydration state, multiplied by bladder tolerance, multiplied by sleep stability. A small sip to take medication is not the same as 600 milliliters. A mouthful after a salty dinner is not the same as a large bottle after drinking alcohol. A person who wakes with a dry mouth because the room is hot and dry is not the same as a person waking 3 times with large urine volumes and swollen ankles in the evening. In 2026, Kaida and colleagues published a controlled study in PLOS One that tested 280 milliliters of plain water immediately before bedtime in healthy middle-aged Japanese men. They compared it with a condition where participants avoided beverages for at least 2 hours before bed. The water condition reduced morning thirst and tended to lower depressive mood scores. It prolonged REM sleep latency and reduced REM duration. It did not improve psychomotor vigilance performance after waking. It also increased Nocturia frequency from 0.24 plus 0.262 to 0.70 plus 0.439 restroom visits. A measurable rise. One input produced both a potential benefit and a cost. The mechanism behind the mood and REM findings is not settled. The authors were careful about that. They suggested possibilities involving hydration state and REM modulation, but the neurophysiological mechanism remains unclear. That matters. The study does not prove that everyone should drink water before bed to change REM sleep. It shows that a modest pre-sleep water load can measurably alter sleep parameters in a specific group under specific conditions. The hardware responded. The interpretation is still under construction. The Nocturia finding is easier to understand. More water entered the system. More urine was likely produced. More participants needed to void. That is not a failure of the study. That is the hydraulic trade-off. Water before bed can reduce thirst and still increase waking. A circuit can have two outputs with opposite value. The same intervention can improve one measurement and damage another. The body is not optimizing for a slogan. Now bring in temperature. During sleep, core body temperature falls as part of the circadian pattern. Heat is moved from the core toward the skin and released. Blood vessels in the skin change diameter. The sleeping environment changes the thermal gradient. A warm room increases evaporative demand. Dry air increases respiratory water loss, because each breath leaves the lungs saturated with water vapor. A fan can increase evaporation from skin, heavy blankets can trap heat and increase sweating. The glass of water before bed may be more useful in a hot, dry, high-loss environment than in a cool, humid room. Salt changes the equation again. A salty meal before bed increases extracellular osmolality. The system detects concentration, not just volume. Sodium holds water in the extracellular compartment and increases thirst. The hypothalamus responds. Vasopressin may rise to conserve water. You drink because the sensor array demands dilution. If you drink a large amount quickly, plasma concentration falls, but the kidney must later dispose of the excess while preserving sodium balance. The result may be delayed. Urine production during sleep. Salt makes thirst understandable, but it does not erase bladder physics. Alcohol pushes the system in another direction. Alcohol can suppress vasopressin release, especially earlier after intake, reducing the kidney's water conservation signal. More water moves toward urine. Sleep becomes more fragmented. The bladder fills while asleep. Architecture becomes less stable. A person may interpret the next morning as dehydration caused only by alcohol's direct chemistry, but the night involved multiple failures, reduced antidiuretic signaling, increased urine output, poorer sleep continuity, and respiratory water loss. Adding a huge amount of water immediately before sleep may reduce thirst, but can load the bladder at the worst possible time. Caffeine is different but still mechanical. It can increase urine production in some contexts and stimulate bladder activity. It also raises arousal. Late caffeine can keep the brain in a higher alert state while the bladder becomes more noticeable. In that condition, water before bed may not be the main cause of waking. It may be the extra load that makes an already sensitive circuit cross threshold. The final awakening is blamed on the water because the water is visible. The invisible part is receptor sensitivity, sleep pressure, and stimulant timing. Age shifts the tolerances. Older adults often have reduced bladder capacity, lighter sleep, higher rates of nocturnal polyuria, and more medical variables. The nighttime vasopressin rhythm may become less robust in some people. The kidneys may concentrate urine differently. The legs may store more fluid during the day. The path from bed to bathroom may carry fall risk. For an older person, the cost of a bedtime water load is not merely poor sleep. It can be a dark room navigation problem with blood pressure changing as they stand up. The hydraulic event becomes a mechanical safety event. There is also the risk on the other side, excessive water. The body can handle ordinary amounts because the kidneys excrete water, but very large intake over a short period can dilute blood sodium. Hyponatremia is not ordinary bedtime hydration. It is a failure of concentration control. The brain is trapped inside the skull, and if plasma sodium falls too far, water can move into brain cells. Swelling inside a rigid container is dangerous. This is why more water is not a principle. It is only more input into a regulated system with limits. A useful way to view the glass is as a test pulse. A small amount before bed sends a small pulse into the fluid control system. If you wake less thirsty and do not wake to urinate, your machine absorbed the pulse without disturbing sleep. If you wake once with a full bladder, the pulse reached the storage chamber. If you wake 2 or 3 times or produce large volumes at night even without drinking, the problem is not simply the glass. It may be nocturnal polyuria, sleep apnea, diabetes, edema, medication timing, high salt intake, or bladder dysfunction. The glass revealed the circuit. It did not create the whole circuit. The evidence hierarchy is clean. The molecular kidney mechanism through vasopressin, V2 receptors, cyclic AMP, protein kinase A, and aquaporin 2 is well established. The fact that excess evening fluid can worsen nocturia is clinically accepted. The fact that overnight water loss occurs is basic physiology. The idea that modest pre-bed water may improve morning thirst and mood has emerging evidence, but the 2026 controlled study was specific and limited. The idea that everyone should drink water before bed for better sleep is not proven. The idea that everyone should avoid it completely is also not proven. The engineering answer is smaller and colder. Drink enough earlier in the day, so the bedtime glass is not doing the work of the entire day. Let the kidneys process volume before sleep. Reduce the late hydraulic load if the bladder is waking the brain. Use small sips if the mouth is dry, not a full reservoir, unless there is a reason. Notice whether the first awakening occurs in the first 3 or 4 hours when deep sleep is supposed to dominate, or near morning, when sleep is naturally lighter. The timing of the wake-up is diagnostic information. The body is printing a log file. When you drink water before bed, Your body does not ask whether the habit is good or bad. It measures. Osmoreceptors measure concentration. Baroreceptors measure pressure. Stretch receptors measure bladder wall tension. The kidney measures hormonal commands. The heart measures volume. The sleeping brain measures whether the incoming signals exceed the arousal threshold. Every part answers in its own language: voltage, pressure, permeability, stretch, flow. So the glass beside your bed is not innocent. It is a control input into a night machine. In one body, it prevents morning thirst. In another, it breaks the first sleep cycle. In another, it exposes a deeper fluid shift problem that was already there. In another, it does almost nothing, because daytime hydration was already stable. The water is simple. The timing is not. You placed the glass beside the bed at the start. Now it should look different. Not healthier, not dangerous, just more precise. A measured volume waiting at the edge of a sleeping hydraulic system. One glass can be a repair, one glass can be an alarm. The difference is the machine it enters.